Good afternoon, everybody. So a couple quick announcements. Today we're going to go through organocatalysis and how it relates over to the selectivity arguments that we've been talking through. Wednesday we're going to do our first class presentation. Just in order to do the screen recording, especially because we're going to have two presentations per class usually, I need you guys to email me your presentation the day before. I'll put it up on the Canvas site and we'll present it off my laptop so that we can switch between people easily. Also, it'll allow me to do the screen recording off of a single laptop much easier. Have everybody's papers up. Those should be all located out, so go take a look. I've linked everybody's paper and just make sure that I've got the right one linked for you. And I will also send out a Google link. It's a survey link basically, which will allow you to complete your review. So everybody's been assigned somebody to do an anonymous review on. I'll repost the the question sheet, the question you're supposed to ask. Functionally, what you're doing is you're going to be evaluating somebody on did they match your SEQA type part. So basically, from your read, did they kind of populate, or what was your understanding that they're trying to communicate? General comments about the presentation content and any things like constructive things for improvement. So just use that link to fill out for the person that you've been assigned to evaluate in. Other than that, yeah, the one quick reminder, because we are, Wednesday's going to be our first dress rehearsal in this one. Everyone else will have 2 in that time. We have to keep the time solid. So basically, you've got a 20-minute, 25-minute block for each person. Can't go over by too much more than that. Any other questions? Okay, cool. Today, we're going to go through kind of bringing it all together in a topical area, and this is just generally organocatalysis. So what this really, or why this features is the different pieces in terms of stereoselectivity, regioselectivity, and rate-based selectivity that we've been talking about, all kind of features in this kind of area. To give you a bit of history, organocatalysis, one of the first ones was the Hajos-Parrish reaction, 1974. This is an example of an intramolecular aldol where it was catalyzed by simple things like proline. Now, again, where this conceptually comes from is people knew that enzymes catalyze reactions, especially if you look at things like catabolic processes that take carbonyl compounds and then extend them. So this is acetyl-CoA and making fatty acid synthesis, or degradations of glycolysis. It's obvious that amino acids have the ability to be central catalysts without any metals. The focus, though, was around this specific activation cycle, where you're actually using enamine catalysis to undergo a nucleophilic bump. Now, what's interesting about this, and we'll focus mostly on this kind of flavor, is this goes back to what we talked conceptually about how all catalysts work, is if you think of it in terms of frontier molecular orbital theory, the addition of the catalyst is either increasing the nucleophilicity, so that's raising the LUMO of some system, it's making it more nucleophilic, or, HOMO, you're raising the HOMO, or you're making it more electrophilic, meaning you're dropping the LUMO. And in fact, there are cases where a single or set of amino acids or organocatalysts can actually do both in tandem, and this is what's led most recently to an area known as tandem catalysis, where you're using multiple things to actually modify both nucleophile, electrophile kind of parts of a system. From a big general, and this is actually from Dave McMillan's Nobel lecture topic, you can categorize all organocatalysis into these kind of buckets. So iminium catalysis is specifically looking at some species where you're actually doing that LUMO lowering. You're making the electrophile more electrophilic or more in tune with whatever nucleophile you have. The enamine catalysis, this is the more things that we're traditionally looking at, things like catalytic aldol reactions, where you're doing nucleophile modification, so that's the HOMO raising. Ammonium is really the same kind of flavor as enamine catalysis. Ylid chemistry, where you're doing formations of things like pK modifications. So this is where you're using hypervalent sulfur, hypervalent iodine to allow you to have a pKa change to get nucleophilic change. So that's again like a HOMO raising. Phase transfer is a little bit weird. It's still an organocatalyst, but usually what you're doing is it's more like specialized ion contact. So you're usually using a phase transfer catalyst not just to modify what is soluble in which phase. So usually you're doing a biphasic system and you're actually using a species like this to selectively dissolve. Think of it like very, very selective soap. hydrogen bonding is kind of another kind of flavor of phase transfer, where what you're doing is modifying the transition state by having some type of an ionic activator or some type of a polar activator associated with it. Hydrogen bonding in particular has been really popular by the Jacobson group, and also the Reed group has looked a lot at this, sort of these chiral phosphoric and Bronsted acids. Last is the carbene catalysis. This is things like the N-heterocyclic carbene, or the CACs, the sort of the carbocyclic carbenes. These are sort of non-traditional mesoionic compounds. And these are more like acylium ions, so things like the benzoin condensation or CO2 fixation. But generally, if you look at the big ones, this kind of progression is what you see. The original stuff was all sort of founded by iminium catalysis, or sort of these kind of LUMO-lowering reactions, modifying the electrophiles, where then enamine catalysis really picked up after. And I think that that's kind of the main areas. The other big one around this too that I want to touch on is what was so impactful about this area was because we now had relatively simple catalysts, it became possible to use early DFT methods to actually validate the transition states that we were dealing with. So this is where Carlos Barbas and Ben List really were in this kind of space, but also they brought in Ken Houck. So Ken Houck is one of the kind of the original organic chemists that's doing DFT computational theory, where they actually came up with some of the first models that predicted stereoselectivity and that matched against this. So again, why it's important is because these molecules were atomically simple enough that the functionals they had at the time could actually properly replicate the stereochemistry that you were actually dealing with. And then now, yeah, Jacobson has really been focusing on this area of using sort of things like thioureas and chiral systems in this kind of component. The original one was, at least from the iminium activation side of things, comes from Dave McMillan. And this was focusing on a Diels-Alder reaction. So the goal here was that at that time, you could take an acceptor, something like an alpha-beta unsaturated carbonyl compound, coordinate it to a Lewis acid would then sort of draw down your LUMO, and then because of that activation, you're just making a better electrophile, which allows your diene to sort of do this reaction. And again, as far as a ring formation, this is kind of one of the key focuses initially of these reactions, because you get to set potentially 4 stereocenters at the same time. So getting some control over this was really impactful, because that cycloaddition is relatively, can be relatively product driven, but it also gives you the really good access to very prescriptive stereochemistry. Now, if you remember back to what we talked before, the different levels of stereoselectivity, calling it stereospecific or stereoselective. This has elements of both, where because it's a pericyclic 6-member transition state, there's a very rigid geometry which allows you to form only certain compounds. Like, yes, you do have your endo and exo approach, so there's an element of selectivity as well, but there's a very stereospecific part where you must have that enforced concerted transition state. So what they found, and again, this was sort of the original FTIR by Dave McMillan in this case. The theory, and if you've ever seen his kind of Nobel lecture, it's actually quite good, because it sort of walks through his early thinking on this and how sort of the projects actually evolved. What he was going through is saying, like, look, if you could go through into this Lewis acid activation, why couldn't you use iminium formation, where you've got this cationic nitrogen, which just meant you had to have an in situ condensation to your aldehyde, which is, you know, potentially possible. It means you have to somehow find a system that by equilibrium, you've got this 1,2 activation across the carbonyl, and not sort of the 1,4 conjugate addition also competing. Or if it is, it has to be something that is under reversible control. So his A/B test was, well, if I just take a simple diene and a dienophile and methanol at some temperature, watching it bioreact IR, absolutely nothing happened for 15 hours. Same reaction, we were dosing in the HCl salt of proline. Now you're seeing not only high rates of reaction, so reasonable turnover, but actually enforced yields. So this was really cool, because there was some early indication that simple secondary amines, you know, you can form these iminiums. This is how we do things like reductive amination. Aldehydes and methanol can definitely make these enamine type systems. What was unique about this is it proved that not only could you accelerate the reaction, so you are doing this iminium activation, but you're also getting some type of stereo control enforced in the system too. So very exciting around that. One thing that I want to keep track of too, and this is something that was kind of early on not as well addressed, but this is something that anybody who's done synthetic chemistry with these nitrogens, the acid activator, adding it with it as an HCl salt became very, very critical. Like you can't just take proline, let's say, on its own and let this reaction happen. You've got to have to go, you are going in with a Bronsted acid as well too. So usually all the early reactions were including things like the HCl salts of these components, mainly from solubility. It was just sort of like I would buy the amine comes as some sort of a salt, and it was just being added. But fortuitously, if you think about the steps that are necessary to actually do condensation between a secondary amine and an aldehyde, those are all Bronsted acid catalyzed processes that we usually see being done by general acid catalysis, right? They're just proton exchange that's necessary in order to populate these intermediates. So the problem with this is it leads to a whole bunch of levels of sort of theory when it comes to selectivity. The general theory at the time was, okay, you've got an aldehyde. The aldehyde is going to undergo a condensation with your secondary amine to make this iminium. So literally all you're doing is taking that nucleophilic center, you're doing your condensation reaction, classic second year bond formation and condensation to make an iminium center. The problem with that is while it's kind of enforced that this is kind of this trans geometry, there are two different regioisomers of that particular enamine, right? So if I do the enamine condensation, and this happens to be a non-symmetrical, so in this case we've got a methyl and your carboxylic acid or your amino acid sort of side chain. You've got two different geometries where you could call it the trans one, where basically hydrogen is on the same side as your amino acid backbone, or the cis one where the hydrogen is facing away, the carbon chain is back into this point. Both are possible, right? Like there's nothing that reinforces that one or the other geometry is going to be the exclusive. You will get both possible geometries, and that's only just the two possible faces of how you might get the cis-trans geometry around this iminium center. There's also possibilities where you could potentially get by what's a reaction known as sort of the Moriata-Baylis-Hillman reaction. This is where nucleophilic addition to your alpha-beta unsaturated system can actually invert it from a fully trans geometry to something like a cisoid one too. So nucleophilic addition, rotation, then elimination means that you're not guaranteed to have that specific geometry. You could have the reciprocal geometry where your starting material might actually be a little bit of something like this, where you have the Z geometry of your alkene as well. So basically the problem you have here is even if you had, let's say, only this specific transition state, that specific transition state, you could model it out and say, if my Diels-Alder is going to happen, one or the other face will be preferable because one or the other face is going to be shielded from that point. What you often see with these kind of starting material geometries, the face that the trans isomer of your activated compound selects for is going to be different than the face that the cis one is. So even if you just used a simple model here to say that this is bulky, that bulky group might be shielding the top face of this trans geometry. Well, as soon as I switch it over to cis, the opposite stereochemistry would be enforced by the opposite component. So really, it's not only about what transition state you're passing through, it's about understanding the population between the geometries of your two different reactive intermediates. So this was an early issue with these kinds of reactions. And again, as far as why did they start here, does anybody recognize where that thing comes from? Yeah, it's just tryptophan, basically. These are the natural amino acids where what they were doing was very simple modifications where we're just doing functional group manipulation, methylating the nitrogen to give you a secondary amine, and then something on the carboxylic acid, just capping it off to make it greasy, something that dissolves into solutions. But they're nice design parameters, right? I can go through and modify those things to get different catalysts. So this is where these kind of ring systems became more useful. So proline obviously is the canonical one that we can start off with. But Macmillan is particularly well known for these kind of imidazolinones, where what you're doing is taking any amino acid, you're then functionalizing it where we're transforming this center into some sort of an amide. It's a bit more stable under most reaction conditions. We're doing a condensation to give us this acetal-like structure, which gives us this rigidified five-membered ring. And as a result of that, we have whatever group or selectivity group we're doing here. We can modify the sterics by what type of ketone we do this condensation with. So this is just from acetone. And potentially you can do other things, which is a bit more remote from this case. This is not usually geography, but you could do things like attachment or other polarity modifiers for solubility. So the real value with this class of catalyst was not only it's something you could tune through, but you could also give you a really strictly enforced geometry where really that sort of extended trans structure was the only iminium structure that persisted. You didn't see that flipped one, so the EZ ratio basically at this imine center was highly favored for the one that you're seeing here. It just means that you have a single population of activated compound. Fun fact from the Macmillan group, everybody that joined the group had a mandate where they had to not only produce a catalyst in some quantity, so you sign up, you have 5 grams of catalyst that you must make every month. That was just mandatory. Talk to Corey about his time on this point like this too. There was a whole bunch of parts of like going through this and saying, you know, part of your job was to go out there and come up with new ones. So basically, since it's a modular synthesis, you just had to go through and try these other permutations to really scope out other kind of component. But again, this meant that a lot could be done very quickly. Going through it, you know, this iminium activation or just changing sort of what looked like this LUMO lowering could be extended out to a whole family of other chemistries where we're just going through the canonical logic that we've done for nucleophile electrophile chemistry and then just expanding it out to include a whole huge variety of things with all ridiculously good enantiomeric excesses. So this was a very valuable space. Now the selectivity behind it, really, if you think about it from the high level, this is kind of the diagram that we would sort of put in place where we're saying, I am making an activated intermediate. I've now restricted it so I have only this geometry of that activated intermediate. That's that enforced sort of extended geometry at this iminium. Now what I have is something is going to add. In this case, let's say I'm adding a nucleophile. In this case, it's going to be just hydroxide. If the hydroxide adds to one face or the other, you could imagine this is under kinetic control, where one of those two faces is going to be favored. The way that we've drawn this diagram, we're predicting that that is going to be your favored pathway to escape. Once again, the selectivity that you get at these two just comes down to the delta, delta G, double dagger, enforced by those two transition state heights. Remember, if this is under something like we talked about Curtin-Hammett control, the really important thing is as soon as that bond is formed, that carbon-oxygen bond, that has to be our irreversible step. That means we're using the relative rate of formation between those two products as your selectivity event. If we go through this, and it just happened that that step right there is your enantiodifferentiation step, if there's any possibility that, because once you hydrolyze that catalyst off, you're down to a pair of enantiomers. There's no energetic difference to the two possible products that you're forming, so this is not something where thermodynamically one of the two products is going to be favored relative to the other. The selectivity has to be enforced in the intermediates of your manifold. So it's possible that this intermediate will be lower in energy than that one, so you can have a bit of a thermodynamic buildup here. But most importantly, we can't climb the hill again. Ideally, that once we've formed our product, whatever your enantiomer product is, we're saying we're not going to be going back to reform some key intermediate. In other words, that carbon-oxygen bond formation in this step must be irreversible. Otherwise, we're just scrambling the whole system. Now, this is one of those cases where if you go through all the literature that's happened here, there's a whole bunch of cases where it maybe seems completely rational that, let's say, the carbon-oxygen bond formation would not be reversible. There's nothing wrong with that part because we're saying that, okay, if it's reversible, we're ejecting like a hydroxide or something like that. Remember, though, we're under acidic conditions. This can sort of look SN1-like, where you've got sort of acid-catalyzed ejection or dehydration, elimination effectively back here, so it is possible by other mechanisms. The bigger one is there's two things that hold that stereochemistry constant, right? You have a proton here. And if you actually look through a lot of the pathways, one of the contentious parts of the organocatalytic world, especially like this, is not only are you saying that the nucleophilic addition is irreversible, and again, that's usually pretty safe. You can measure the delta H of what that bond forming is. The bigger problem is that you're never forming something that has an sp3, sp2 conversion. In other words, we're not deprotonating that center to go back to an enolate or something else like that. And that's a lot more difficult because if you look, there's ways that you could draw out this pathway where you're just doing an oxidative shuttle. These are like beta hydroxy ketones where deprotonation to form a different extended structure may actually be possible because you do have access to these kind of extended enolate or iminium type systems. So what seemed weird by a lot of this, and it does come up quite a bit, is somehow you're setting a stereochem center where the product geometry is now not possible to re-enterate enamine or enolate type systems, right? You're never making something where you're destroying that other proton, which would then destroy your stereochemistry. It's something I'll comment on in a couple of specific ones a little bit later. The real big one when it came down to computational geometry was this. It was called the Hauck-List model. So this is Ken Hauck and Ben List. And really what they did is they took inspiration from, you guys are probably familiar with the Zimmermann-Traxler model, right? So if you know the addition of an enolate into an aldehyde, we know that the geometry of that forming cycle, or that the aldehyde as it approaches, you have your pseudoaxial and pseudoequatorial approach. So where this group of your aldehyde goes is kind of dictated based on a six-membered chair-like transition state. So they started with that concept. What they found is, in the case of proline, you had two interesting things. Not only are you getting the facial selectivity of this aldehyde enforced by this kind of Zimmermann-Traxler-like model, but remember, the green guy here, that is one plate, that's one sp2 sort of center. Your red one, that's your aldehyde, that's your second sp2 center. You're back to having this molecular patty cake, right? There are four possible combinations you could run into. So even as I've drawn here, if the green is in the plane of the page, and the red is outside, we're showing this specific geometry here where we're bringing green and red together, where we're just enforcing a single geometry of that arrow group. We could flip it over, and now what we have is pseudoaxial, pseudoequatorial, but we're still attacking the same face of our green group. And then vice versa, you have the other two on the other side. So all four possible combinations come from the ray, C ray, and all combinations from that point. So even if you said, okay, arrow group is going to be in the pseudoequatorial plane, front face versus back face is the thing they had to control. And really the key about the Hauck-List model was that when you used proline, where you've got this Bronsted acid built into it, the proton from proline exists on one face of that proline group. So what we're trying to emphasize here is that not only do you have this chair-like transition state baked into here, that chirality means that you've got this simple carboxylic acid which donates a proton and effectively brings the electrophile in preferentially from, in this geometry, from the front face. In the same one, if that proline group does not rotate over to the back, or if it did, in this specific geometry rigid out, we're saying proline from the front becomes how we get an antioselectivity between these two. So the general model as accepted initially was you start with your proline, you do a condensation to make a starting iminium. That iminium is acidic about this center. So the nucleophile, the enamine here, is just an acid-base reaction. Having this kind of Bronsted base nearby means the proton can be temporarily shuttled over to that carboxylic acid. Now that you've got this, there's kind of two really key things about this geometry. One is the nucleophile exists as this enolate. In other words, the nitrogen and the R group sit on opposite sides. So you have this trans enolate. It's not the R on the same side. That's one mode of control. Two, once I've got this geometry, this group here is preferentially bringing an electrophile in from the same face as that carboxylic acid. So it becomes a agostic interaction bringing in this hydrogen. What you get from that addition, again, if you just follow your arrows, right? Lone pair comes down, lone pair attacks, you get a product iminium. And this is where the first weird one comes in. If you look at your product iminium, what you're saying then is in this one step, I need to hydrolyze that bond super fast, because if I don't, I have a proton right there that I could deprotonate. If I deprotonate that center, I've just destroyed the chiral center that I put for my R group. I haven't destroyed the alcohol, right? The alcohol center is stable, so I still have a pair of diastereomers here where that facial selectivity of the red aldehyde has been enforced by that carboxylic acid. But this is one of those first key things where effectively you might be epimerizing at that center. Now what that just means is the diastereoselectivity of your product would be eroding over time, because if you take your product, give it back to proline, You're just racemizing that center through condensation and acid base. But again, this is one of those cases where there seem to be some interesting parts to this because the enantioselectivities you're getting were enforced by this. How could take any amino acid, any aldehyde, and any secondary aldehyde, you could put this all together and you could reasonably tell you within pretty tight tolerance what the enantioselectivity of a reaction would be. In fact, that's what sort of was one of the really key links in this one. It was one of the first times that Hauck could say to List, this is what I think your enantioselectivity is going to be. List could run that reaction and come back and say, yes, you were right, that matches your model. There's a whole bunch of other things under that one too. There's cases where solvent effects were not properly captured. There's a lot of cases where theory did sort of, there was a miss. But what was super cool about this, it was the first time that theory could sort of say, this is what you have to go and get. When experiment didn't line up, it became this big blinking thing of something else is happening here. Let's go see what's going on experimentally of why it's deviating from this sort of model. So it was a really critical part for sort of early DFT and stereoselective predictions. Just to show you all the possible geometries. So in this specific ketone addition, you get these two possible enolates. These are the two enolates you get from just addition to a ketone. So we're just showing sort of the trans and cis geometries at this alkene. From there, you have two possible facial approaches, front or back faces, which gives you all these possible products. So this is sort of just the extended geometries that are possible as you go through it. So this is one of those cases where if you look at the complexity that might happen in these sorts of systems, it's actually pretty awesome that we do get the stereoselectivity, both enantio and diastereoselectivity that we do. Now, back to sort of the, let's say the rationalization at the time. Herbert Eschenmoser was one of the other major players in this area that was learning about this. And one thing that they noticed, and again, if anybody's run this reaction, typically these reactions are run in things like toluene. You're running them in very apolar solvents in a lot of cases, sometimes in things like DMF. So what you get is something where the addition actually does not proceed through these aminiums. If you actually watch this reaction, you never actually observe that structure or this structure. And that doesn't totally surprise you. If you look at this and if you're running these in things like toluene or hexane, completely ionic structures like this are not likely going to be very stable. They might be there, but they're going to be ridiculously high energy because of the system that you have. In fact, though, what you could observe were these. So these are the oxazolidinone derivatives of these. All that happens here is if I take this nucleophile here and attack that center, you make these kind of closed ring systems. So you can think of the oxazolidinone as the it's a covalently bonded version of your aminium. It has the same basic properties, right? This is the same thing as saying that I have the sp2 versus the sp3 version of the same oxidation state at that part. It just happens that the oxazolidinone centers are, or oxazolidinone structures are going to be much more prevalent in solution. So there was a general debate of, well, what's actually happening under the hood? Are you actually doing sort of like E1CB kind of mechanisms where the oxazolidinone is on the cycle, you have proceed through that one, versus saying, well, really what's happening under the hood is you're only going through the aminium centers, it's really only acid base, and these were parasitic compounds. Basically, they're existing off the actual catalytic cycle, and they're just a stable form that's not really relevant or not productive. So the kind of two competing theories were something that was happening for quite some time. In the end, you're still getting the same kind of general ideas that the geography and geometry of this enamine is still what's setting the actual overall stereocenter. But the pathway is something that really was something to be focused on. So what happened in what year was this? 29? Sorry, up here with the DOI? Yeah, 2009. Good stuff. There was the first NMR proof that could actually look into this. And I wanted to highlight this because it's another really interesting sort of dynamic experiment that can be used. And it was done by a researcher called Ruth Geschwind. She is by far one of the the best physical organic NMR people I think that's in the field right now. So still doing a lot of really, really powerful work. But this was her first big splash. What she did is she went after the very simple proline catalyzed aldol. Even though people had been sort of talking about it, it was all pretty much based on isolation of individual intermediates and an observation of isolated compounds. This was one of the first dynamic experiments that she did where she's looking at the live system as a system with all interconverting compounds and then looking at what's happening as a process. So first, she was doing it in DMSO. She ran it with the simple proline systems, and she's just doing the self-aldol condensation with just propanal. When this is happening, you're seeing the conversion. And if you notice this shape here, that's a very classic sort of second order curve where you're getting this very precipitous drop of material, so that looks good for like a condensation. You're getting the formation of the aldol products, so these are the two different diastereomers of the aldol products, and also the aldol condensation product. That's just keeping in mind that as the reaction's running, you're dumping water into the system, so the solubilities are changing as well. What was more interesting, though, is if you go down into the baseline, so these are the major components at relatively high concentration. These minor components were, in fact, the aldol oxazolidinone structures. So these are those surrogates for the iminiums and the enamines that we talked about before. But also, it's the first actual quantification and observation of a proline enamine in the context of the reaction. It was the first time they actually observed this. And part of the problem here was they're super low concentrations, they're very reactive, you can't isolate this easily, but on top of it, these are pretty messy systems. If you try to actually deconvolute a reaction like this, you have not only the low concentration of this component, but you have so many other very similar, structurally similar ones. So proton and carbon NMR of these systems is very difficult. How she did it was using a really cool technique called XE. Have you guys ever heard of XE? So, University of Ottawa. He's now retired, but his name was Glenn Facey. Glenn was the biggest NMR nerd I have ever met. Phenomenal teacher. He still has this up available. So if you go to the University of Ottawa NMR facility, there's this huge blog that tells you about how you really do NMR well. So this is like quantitative conditions. This is if you can't see a cross peak, try these sorts of things. It's a phenomenal sort of tool for using NMR to exceptional effect. He wrote this one specific one too on what 2D XE is and how it works. The reason I bring it up, one, is it's super powerful. Two, it was actually invented and popularized by Charlie Perrin, who is David Perrin's dad. Charlie Perrin used this technique to actually work out the structures of things like proteins in equilibrating systems, so it's for dynamics. How it works, basically, is in a normal NMR technique, I put in magnetization at a center and I'm looking for a resonance pattern of if I irradiate, do I get these protons absorbing? How the 2D XE works is it's kind of like an NOE, where what you're doing is a proton pulse, you wait a delay time, and then you do an observation. Now, normally for NOE, we would be irradiating, let's say, here, and we're looking for through space magnetization to some other part, and that usually happens where those are opposite phase, right? So if I have energy putting into one center, I'm looking for an opposite phase correlation, which is my NOE transfer through space to magnetization transfer. What XE is, though, is I put in energy here, where, let's say for this case, because these two are effectively diastereotopic methyls, those two methyls will have two different chemical shifts. Turns out that compound 1 would be resonating right here. What I can do, though, is I can put an energy at that frequency. If I wait a period of time, which is equal to the rotational frequency of that bond, it will then dump its energy at the second frequency. So what I'm doing is I'm adding energy to a proton, I'm waiting for a dynamic event to happen, usually as part of an equilibrium, and then I'm observing that same energy now as being released at a new frequency due to whatever environment it's now into. So what you're doing actually is, if I slowly walk up this, this time, I can basically measure the K1 and K-1 of that equilibrium for that rotational dynamic. Now, it does not always work. There's lots of reasons that XE will fail, but it's really good at measuring both the forward and backward rate constant of these relatively fast equilibriums. Not for it's like a single transition, usually in this case like single bond rotations or single conversions within certain K values. It's exceptional. Again, this is where it was primarily used for things like protein dynamics, so rotation around amide bonds or sort of folding and unfolding geometries and stuff too. You can couple this XE technique with all sorts of like carbon, hydrogen, carbon, nitrogen, everything else you could normally do, but it's still this pulse probe kind of an idea. So what Ruth did was this technique. One, she was able to take the really, really ugly spectra, and she could selectively irradiate the aldehyde of the free propanol and then watch by XE where that proton went after it had been converted. So think about it, what she's doing is she's targeting the free aldehyde, she's putting energy into the free aldehyde CH at the sp2 center, and then she's watching that energy be released once that aldehyde has condensed to turn into either the oxazolidinone, either of the two oxazolidinones, or into the enamine. So what she did is, through this point, she was able to identify all the other spectra that were associated. So she's pumping into this one, and she's watching the formation of each of these other sort of compounds. So it just allowed her to go through and just use that chemically diagnostic CH as a technique for looking for where these other compounds had. What she observed, though, was that finding the direct peak from the aldehyde to the enamine was actually kind of hard. Instead, what she found is the aldehyde seemed to be directly correlated to those two oxazolidinones. If you pulsed on the oxazolidinone, you could, in fact, get the enamine. So what that kind of reads as, you're not seeing, if you put energy into the aldehyde seems to transition first to either of the two oxazolidinones. From the oxazolidinone, then you transition to the enamine. So there's not a direct equilibrium from aldehyde to enamine. Aldehyde goes to oxazolidinone goes to enamine, which still fits with the general theory we said that the condensation is kind of going to something kind of like an iminium structure first before you do the acid-base deprotonation. So it's still getting this point. But this is effectively what she kind of sketched out, that the condensation went by this kind of sp2 to sp3 transition, and then some type of elimination event seemed to be most probable. There was one more piece of math that I really liked what she demonstrated. She looked at the two pathways and said, okay, on the left, you have this kind of stepwise pathway where potentially your proline and your aldehyde is going to do an addition to make either of these two compounds. The selectivity of which oxazolinone you make is just based on the stereochemical energy. It's this thermodynamics to say which of those two is more favored. And I believe that the top one is favored over the bottom one just because of the geography of that five-membered ring. You have a stereocenter at the top next to the carbonyl from the nitrogen. Then what you're getting is a collapse where it doesn't matter which of these two you have, you're destroying that stereocenter, so they both kind of recollapse together. So what you have here is a cyclic series of equilibria that everybody is related to each other. This is what's kind of known as Onsager's triangle. What we mean is it doesn't matter where I start on this cycle, the equilibrium constants as you move around, you have to go and get back to the same place. So imagine I'm starting here as the aldehyde. I could have a 4-to-1 selectivity between my two products, but then both of those are going to collapse back together the same compound. It means that all of them together, it doesn't matter if I start at this bottom cycle over here, eventually I will populate this whole system based on the relative equilibrium that are present in the whole one. It's connected. What it means, though, is if I have this system, if I had this one over here where I'm going through a common intermediate that connects everybody, then the ratios of all those things must be constant. And what I'm saying is, it doesn't really matter if I'm coming from the oxazolinone at the top or the bottom. Because I'm going through a common intermediate, the relative ratio of the population of starting materials and products must be the same. So this only holds if you have that particular geometry, where the ratios of the equilibrium constants across here must be equal no matter which way you come from it. What she found was that those ratios of equilibrium constants were not equal. In other words, what's happening is you're saying going the top route versus the bottom route, you always had this kind of 4-to-1 selectivity, versus if this is a common intermediate, these should all be equal to each other. That's the only way that those would make any sense. So mathematically, it seems to prove that this is actually what's being held. You're getting this fractionation where both of those are recombining back into an enolate structure. The other thing that this really proves, so first of all, XE is a very useful technique for doing this diagnostic walk up your time constant in order to watch your equilibrium constants. You can approximate your K values. What she's doing here was actually a modified Rosie experiment. So this is a single shot 2D experiment, not a whole bunch of 1Ds. And then from that, you're getting these cross peaks. Those cross peaks on your two-dimensional structure can actually be integrated. That integration can be quantitative. So it's just a reminder that when you do things like your COSY or these other ones too, it's more than just, oh, I have a dot there. That dot and the size of that dot is a quantitative peak that you can integrate in the same way that you would normally do for one-dimensional proton as well too. So what it seemed to prove is that this parasitic equilibrium one is actually incorrect. The oxazolinone is actually endemic. It's on part of the cycle. It's really, really important for how these actual systems move forward. And it did update what the Hauck-List model looks like. The last thing I want to mention, though, is something I'm going to leave you guys with to look into. So the Hauck-List model works because what they're saying is I have a group which synergistically brings in my electrophile. And while it was built for the aldol reaction, it seems to apply for any proline enamine nucleophile. In other words, I can take an aldehyde, I can make my proline enamine. That proline enamine, doesn't matter if I'm talking about an addition of an aldehyde as my electrophile, or if I'm bringing in something like N-bromosuccinimide, anything that generically was some type of a sigma or pi electrophile seems to have this proton-assisted way to bring it on one side. That's kind of the kind of common point. The other flavor of these reactions are what are known as these kind of prolinol systems. This is where what you would do is take proline. You'll add 2 equivalents of a Grignard to the aldehyde or the carbonyl center of your proline, and what that's doing is you still have this tertiary alcohol, but it's no longer nearly as acidic, so it's not being used as a donor anymore. Now what you have is these really bulky aromatic groups, which is acting under steric approach control. Generally, the canonical theory was if you went from proline to these kinds of structures, you're going to start inverting the stereoselectivity. You're going to be choosing from the other face because the same kind of population of enamines now has this large bulky group which brings the electrophile in from the opposite face. So this becomes the other side. The real core part of this, though, was now you've lost this ability to form these oxazolinones, those kind of the structures we talked about back here, where we're like, okay, as long as I have that nucleophile electrophile system, if I've got this ionic contact, collapsing to something like the oxazolinone is actually possible, and from everything else we've seen mechanistically, that's actually really, really necessary under polar aprotic kind of systems. You have to actually pass through this one where the enamine structure is actually too high energy to actually access. But if we switch over to these kind of Hayashi kind of catalysts, these bulky ones, you can't access these anymore, so what's going on here? You've actually perturbed the system in a way that you've lost what seems to be a really critical one, and going back to form these iminiums didn't make sense. So this was a study done by Donna Blackman and Jordi Burris, looking back at these kind of systems, and what they found is, this is in this case, an aldehyde addition to these nitrostyrenes. So it's now you're replacing the electrophile. Instead of being just a simple aldehyde, it's now these electrophilic nitrostyrene kind of systems. You're still going through some kind of a secondary amine nucleophile case, so you're still forming some sort of stereoselectivity. There was a couple interesting smoking guns they ran into, and this is something that if you've ever done these reactions, you may have seen this. Taking something like a doubly substituted aldehyde, there is almost no reaction whatsoever. That seems to kill this chemistry altogether. Even though it has an alpha proton, conceivably you could make an enolate there. And if this was drawn as simply as we'd drawn before, there's nothing necessarily in terms of the pK that says that that's not possible. But there's something really interesting about that case where the other part too is you do get some of this product, but it turned out that the concentration of product exactly matched the concentration of the catalyst that you added. So there's something happening here where you can make enamines, but it's no longer catalytic. It's not that you can't make the nucleophilic structures. What was missing now is something about necessary for the overall catalytic system was now dead just by having that second addition here. And again, really what we're saying there is this actually comes back to a relook at this system. What I'm going to do is I'll leave it with you, but they ended up proving that the entire selectivity of these systems was based on a Current and Hammett model, not based on a steric approach control. The quick hand waving part said that pathway A, pathway B of why you get one face versus the other was just a matter of, okay, one of the two faces is blocked, one face can be hit by the electrophile faster versus the other. What it turned out was going on here is that these systems form these ridiculously stable intermediates, and the relative population of those intermediates and the rate at which they can hydrolyze is actually what's under the hood for this whole system. It's not something I'm going to go through in any other detail. Just wanted to mention that if you're interested, if you are doing things like organocatalysis, the new model that they proposed a couple years ago actually really gives you a much better predictive model for how these systems work and how to actually change your conditions to use these to much greater effect. So if it is something you're trying to set as stereochemistry by these kind of proline and prolinol kind of systems, the experimental update that they did is really in your favor. Okay, I will see you guys on Wednesday.